Well, this is our final review for AP Calculus. We're going to take a look at questions 1 through 5 in this video, starting with question 1. So the problem here says to locate the absolute minimum and the absolute maximum of the function. So we can see that right about here, we have the maximum of our function, and that you should be pretty familiar with that from your work with algebra. This is just, well, it looks like it's just a parabola. So that's our maximum over there. We would say that our maximum is at the coordinate 2, 3. And we could also say that our maximum is 3. Now notice that the maximum refers to the y-coordinate. So the y-coordinates have a maximum at 3. For the minimums, we can notice that this parabola actually continues going down. So on the left side of the vertex, the left side of this parabola, the y-coordinates continue to decrease. And that same thing is true on the right side of the vertex. As the x-coordinates increase, the y-coordinates continue to decrease. So we would say that there is no absolute minimum here as well. There's also no local minimum, but I think this question, as you're reading it, it says absolute minimum over here. So there is no absolute minimum. And that brings us to question 2 here. Determine whether the function f of x equals the cube root of x satisfies a hypothesis of the mean value theorem on the interval from -1 to 3, or explain why it does not. So for this question, you are going to have some kind of a knowledge about how the cube root function looks. In my brain, this is a function that I think about when I think about the cube root of x. Naturally, you should have this memorized. And the reason why we need to know what this function looks like is the question that we're really asking right now is whether or not this function is continuous on the interval from -1 to 3. And if I just consider the piece between -3 and 1, if you can see it's just this blue portion right along here, then yes, certainly that function is continuous. We can draw that without lifting up our pencil. But now let's consider the other part of the mean value theorem where the function needs to be differentiable. So let's figure out our derivative. If y is equal to 1/3 of x, then dy dx is going to be 1/3 x to the -2/3 power, which can be simplified into 1/3 times the cube root of x squared. Which means, since x is in our denominator, x cannot be equal to 0, otherwise my derivative is undefined. So this is not differentiable at x equals 0. So f of x is not differentiable on -3 to 1, which means that we cannot use the mean value theorem on this function if we're going to consider values in the interval from -3 to 1. Okay, let's go on to the next question. Our next question is to find all the local extrema for the function f of x equals the cube of x minus 4. And this is kind of a classic calculus problem because we just need to apply either the first or second derivative test here to find our local extrema. Our first consideration is to say that the function f of x is continuous for all x's between -infinity to +infinity, which means that we don't have any place which would be either a cusp or a break. So we can purely look at critical numbers as places where the derivative is equal to 0. Speaking of, where are those other critical values? So let's remember that the derivative of the cube of a function is always 3 times the function to the second power multiplied by the derivative of that function. so even if you're not thinking of it, you do have to figure out that derivative of x minus 4, which is, of course, just 1. So my derivative is 3 multiplied by the quantity x minus 4 to the second power. If I set that equal to 0, we get ourselves a critical value when x is equal to 4. Now, I'm always tempted to go ahead and do a second derivative test in this case. So let's see what happens if we try the second derivative test. We get our second derivative is the 3 from the first derivative multiplied by 2, which is the power up here. And then we're going to take our function x minus 4 and decrease the power to 1, multiplied by the derivative of x minus 4, which is, of course, 1. And so my second derivative is 6 multiplied by the quantity of x minus 1, which is a problem because we can't use the second derivative test on this, because the second derivative test requires that we have a second derivative that is either positive or negative at our critical values. So I think at this point, a lot of students will say that the second derivative is kind of useless because, well, we'll get these cases where the second derivative is going to be equal to 0. But I don't want you to lose heart on the second derivative test because it can be used in a lot of cases. And in those cases where it can be used, it's actually a very useful test to have, very quick results. So there we go. We can't use the second derivative test. Let's use the first derivative test. So the first thing we'll do for our first derivative test is set up a chart where we look at values of x. And make sure you label your chart, that way that whoever's reading your paper will know what you're doing. I can't assume, reading your paper, that you mean these to be intervals for x and not, for example, intervals of y. Next, we'll be analyzing derivatives at places between or in these intervals. Again, label your chart so that we know what you're analyzing. So if we analyze our first derivative from negative infinity to 4, let's pick a convenient place here. Let's just say 0. So we have our derivative at 0 is going to be equal to 3 multiplied by the quantity of 0 minus 4 to the second power. And remember that I'm not interested in what the actual value is. I'm only interested in positive or negative. So if I imagine I square something, regardless of what's in there, I'm going to get a positive result. So this is actually positive. And that brings us to our second interval over here from 4 to positive infinity. Let's imagine substituting something in there. I always like to think of, if I can't substitute 0, think of a really big number to substitute, because things become a little easier to analyze. So my classic is at 100. This derivative is also greater than 0 for the exact same reason. You're squaring a value and then multiplying it by 3. So it looks as though the first derivative does not change from positive to negative or negative to positive. And so since the derivative does not change signs at our critical values, there are no local extrema. Remember that local extrema only will occur at critical values or at places where either the left endpoint or the right endpoint of our domain. So since none of those exist, we don't have any critical values. Okay, let's take a look at the next question, number 4, which would be to find the function with the derivative x minus 3 that passes through our point 3, 3. We have a couple of options for solving this problem, and I'm going to start with the option that seems easiest, the one that definitely I probably used when I was in school. So we start with the antiderivative of x minus 3. That gives us 1/2 x squared plus 3x plus constant of integration. And then we say when x equals 3, we get a half of 3 to the second power plus 3 times 3 plus our constant of integration is equal to 3, which is equivalent to saying that 9/2 plus 9 plus constant is equal to 3. And then now we'll do some quick solving. Well, you know, quick in quotes there. We got 9/2 plus 9 plus constant is equal to 3, which is the same as 9/2 plus 18 over 2 plus 2c over 2 is equal to 6 over 2. So 27 plus 2c over 2 is equal to 6 over 2. Equating the numerators, we get that 27 plus 2c equals 6, which means 2c equals negative 21, and c is equal to negative 21 over 2. Ultimately, this means that y is equal to 1/2 x squared plus 3x minus 21 over 2. Remember, the answer to this, or the solution to this differential equation, is not the value of c, it is the function for y. That's option 1 for solving this. And again, like I said earlier, this is probably the way I would have done this when I was in high school. Option 2 would be to use the definite integral. And this is not the way that I would have done this in high school, but it is certainly valid. For this method, we're going to use, firstly, the fundamental theorem of calculus, and secondly, the knowledge that f of 3 is equal to 3. Now, f of 3 is a little bit weird to say here because looking back at our function, or our problem here, there's no f here. So we have to make the silent agreement that y is equal to f of x. And then over here, we also have to say that f of 3 is equal to 3 from this right here, the fact that our function goes through the point 3, 3. So you're going to see that this is exactly the same thing. So on the left side, of course, we're going to find our antiderivative. Not a problem. The antiderivative of t plus 3 is 1/2 t to the second power plus 3t. Since this is a definite integral, we don't have to worry about the constant of integration. And on the right side, we're going to remember that f of 3 was just equal to 3. Now we have this set up, and we can make our substitutions. So we're going to start by substituting x. So we have 1/2 x squared plus 3 times x multiplied by 1/2 of, now we're going to substitute our 3. With our substitutions made, we're going to maintain that equality with f of x minus 3. And we're going to simplify here on the left side. We'll start with 1/2 of 1/2 of 3 squared. And then we'll simplify 3 times 3. Do a little simplification on the left side, or 3 times parenthesis x is not very sightly. And then we'll simplify 9/2 plus 9. Okay, that looks great. The only thing we have to do next is to add 3 to both sides to complete the transformation. And then combine negative 27 over 2 plus 3. And there you have it. The function is, for the antiderivative, is 1/2 x squared plus 3x minus 27 over 2. And then the last problem we'll do for this video is number 5. Find all the inflection points for the function x cubed plus 3x squared minus x equals 24. Inflection points mean analyzing a second derivative. So we'll need to get to the second derivative of our function. We're going to go through this pretty quickly, just because you should know how to take derivatives by now. We've got y prime is the same thing as dy dx, which is 3x squared plus 6x minus 1. Remember that the proper notation for the second derivative is y double prime, or d squared y over dx squared. That's going to be equal to 6x plus 6. And at this point, we can solve and make that equal to 0. And we know that this is going to happen when x is equal to -1. But you might be tempted to, at this point, just answer with a -1. And remember that in order for something to be an inflection point, that second derivative really needs to change sign from positive to negative. So we need to do a quick check just to see that that second derivative in fact changes from either positive to negative or negative to positive when x is equal to 1. Just like last time when we did the first derivative chart, make sure that you are notating. We're saying that our first line is f is x, and our second line is going to be the second derivative of x. So let's check our second derivative of x for any number between -infinity and -1. 0's not included in that interval, so I'm going to use -100. So let's see, our second derivative is going to be 6 multiplied by -100 plus 6. And yeah, that's going to be a negative result, so less than 0. Let's check our second derivative for any number between -1 to positive infinity. And this time we can use a 0, so I'll just use 0. We got 6 multiplied by 0 plus 6. And of course, that result is going to be greater than 0. And finally, since we notice that the concavity changes at x equals -1, we can say that there is a point of inflection at x equals -1. Now, the only thing I need to check is to see if they want this in a coordinate or the x coordinate only. And reading the problem, it says to find all inflection points. So the inflection point is an x coordinate and a y coordinate. So let's get the point of inflection. If the x coordinate is -1 and I substitute a -1 into my function, so we get our y coordinate is -1 to the third power plus 3 times -1 to the second power minus a -1 plus 24. Let's copy that and simplify it. Starting with -1 to the third power. -1 to the third power is just -1. -1 squared is 1, so 3 times 1 is just 3. So now we've got 3 minus a -1. That's the same thing as just plus 1. So we've got -1 plus 3 plus 1 plus 24. That looks like 27 to me. That's 27. So our point of inflection, let's write that point of inflection is -1 and 27. And that does it for our first video. We'll see you for the second one, where we do, I think it's going to be numbers 6 through 10. And see you next time.